Okay, so good day to our dear Math Science High School students. Let's try to continue answering one of the problems on our lesson for the third lesson for the first quarter on Polygons. Okay, so for the third one, what is the number of sides of the polygon? Now, for this problem, we still don't know what the polygon is. We're trying to determine it based on the given information that we have. For the first one, the sum of the interior angles of the polygon is 4 times the sum of the exterior angles. Now, we know that the sum of the interior angles of a polygon is equal to 180 times n minus 2. And it says here it's equal to 4 times the sum of the exterior angles. So we know that the sum of the exterior angles of any polygon is just a circle, right? Okay, so let's say for example you have a pentagon. Okay, so if you add all of those exterior angles, okay, if you add all of these exterior angles here, so it's gonna give you a circle. So that's 360. So 4 times 360. Okay, so this is gonna give us 180. N minus 360 is equal to 4 times 360. And what's 360 times 4? We're going to multiply that. So that should give you 1,440. Okay, now solving for the value of n, or the number of sides for this one. So this is going to give us 180n is equal to 1,140 plus 360. 1,440 plus 360, so that should give us 1,800. So 180n is equal to 1,800. And if we're going to solve for the number of sides, we have to divide both sides by 180. So therefore, this is a decagon. It has 10 sides. Okay, so most likely it's a decagon with 10 sides. Okay, so the data is sufficient. Okay, just by examining this given, let's see if the data that's been given to us is sufficient for the second given. The number of diagonals in the polygon is 25 greater than the number of its sides. Now, there's a formula for finding the number of diagonals in a polygon. So D, that's the number of diagonals, is equal to n times n minus 3 divided by 2. Now, the given here states that the number of diagonals, okay, so the number of diagonals is actually equal to 25 greater than the number of its sides, or it could be n plus 25. Okay, so since D, both of these D's are diagonals, and they're just referring to the same polygon, okay, so let's try to equate them. So quantity n minus 3, quantity n times n minus 3 divided by 2, okay, is equal to n plus 25. Okay, so solving for the value of n, we can transfer n to the other side. So n times quantity n minus 3 all over 2 minus n is equal to 25. Multiplying both sides by 2 so that we can cancel the denominator 2 here on the left side. So it's canceled. So this is going to give us n times n minus 3 minus 2n. Yes, we have to distribute the 2 there on the outside part of the parentheses. So that's equal to 50. So let's try to simplify this. So this is n squared minus 3n minus 2n is equal to 50. Okay, so that means we have n squared, okay, minus 5n minus 50 is equal to 0. Now, how can we factor this trinomial into two binomials? So we can use the quadratic equation, but as we can see here, this can be factorable. Okay, so it's quite factorable for this one. Okay, so if we're going to draw a solution for it, so it could be that we have the values n minus 10 times n plus 5 is equal to 0. Okay, let's check if these two binomials give you this trinomial. Okay, so we have n minus 10. Okay, we're just gonna check times n minus 5. Okay, so let's use the FOIL method. The first terms, okay, remember the FOIL. First term, outer term, inner term, and then last term. So we have first term that we have to multiply the outer term, the inner term, and then the last term. Okay, so we have the first term, so that's n times n, so that's n squared. Then we have the outer terms. Okay, so that's negative 10 times negative 5, so that's oh no, this should be positive 5. So this should be negative 50. Okay, so we have the inner terms. So negative 10 times n, so this is negative 10. Okay, and then the last terms, 5 times n, so this is positive 5n. So negative 10 plus 5n, so that should give you negative 5n. And then we have your n squared minus 50. So since this trinomial is identical, or it's just the same as this trinomial, this trinomial. So there you go. So they're the same, and therefore you're quite sure, you're 100% positive that these are the binomials for this trinomial, and we can find the roots of this. So n should be equal to positive 10, or n can be negative 5. Since we cannot have negative sides in Euclidean geometry, therefore the most possible answer would be positive 10. So therefore, both evidences provide sufficient, both given data provide sufficient evidence for this polygon to be a decagon. And that's how we solve this problem.